The landscape of data storage has undergone a dramatic evolution, transforming from bulky, slow, and prohibitively expensive systems into the compact, fast, and remarkably affordable solutions we rely on today. This journey reflects a relentless pursuit of efficiency and capacity, driven by an insatiable global demand for data. The digital age fuels this demand, leading to an explosion of information across businesses, individuals, and scientific endeavors worldwide. Every click, transaction, and scientific breakthrough generates new data, requiring increasingly sophisticated methods for its preservation and retrieval. Understanding these evolving technologies is not merely an academic exercise. It is crucial for anyone involved in managing and utilizing data effectively in our interconnected world. Our exploration begins with the foundational technologies that shaped the early days of digital information. These traditional methods laid the groundwork for everything that followed, even as their limitations pushed innovation forward. Examining their principles provides essential context for appreciating modern advancements. Magnetic storage, primarily embodied by hard disk drives or HDDs, stands as one of the earliest and most enduring forms of digital storage. These devices store data on rapidly spinning platters coated with magnetic material. Read and write heads precisely move across these platters, altering magnetic polarities to represent binary data. HDDs offered revolutionary high storage capacity for their time, at a relatively low cost per gigabyte. This made them indispensable for personal computers and server farms alike, forming the backbone of early digital infrastructure. However, their mechanical complexity presented inherent disadvantages. HDDs are susceptible to physical damage from drops or impacts, and their moving parts limit their speed compared to electronic alternatives. The constant movement of platters and heads also means higher power consumption and greater noise output. Despite these drawbacks, HDDs continue to play a vital role in large-scale archival and cost-sensitive storage scenarios. Alongside magnetic media, optical storage emerged as another significant traditional technology. This category includes familiar examples such as compact discs, CDs, digital versatile discs, DVDs, and Blu-ray discs. Optical storage utilizes lasers to read and write data onto a reflective surface, typically a polycarbonate disc. The primary use for optical media has historically been archiving and distributing data, from music and movies to software and backups. They offered a portable and relatively inexpensive way to share information, making them popular consumer products for decades. This portability also lent itself well to long-term physical archives, though their lifespan can be limited by environmental factors. However, optical discs suffer from slower access times compared to both magnetic and solid-state drives. Their capacity, while significant for their era, became a bottleneck as data requirements grew exponentially. Despite their declining prominence, the principles of optical data manipulation continue to influence specialized data storage research. Moving from traditional methods, we arrive at the era of modern storage technologies, dominated by solid-state drives. SSDs represent a significant advancement, fundamentally changing performance expectations for digital storage. They utilize flash memory to store data on integrated circuits, akin to the memory sticks and cards found in cameras and phones. The key distinguishing feature of SSDs is the complete absence of moving parts. This design choice brings numerous profound advantages over HDDs. SSDs offer dramatically faster access times, allowing operating systems to boot in seconds and applications to launch almost instantly. Their solid-state nature also provides vastly improved durability, making them far less susceptible to damage from drops or vibrations. Furthermore, SSDs consume significantly less power and generate less heat and noise than their mechanical counterparts. This makes them ideal for laptops and other portable devices where power efficiency is paramount. SSDs have seen increasing popularity across both personal computing, and enterprise use cases. They are now considered critical for operating systems and any applications where speed is vital, such as high-performance databases, video editing, and gaming. The performance gains offered by SSDs often translate directly into increased productivity and responsiveness. The primary disadvantage of SSDs has historically been their higher cost per gigabyte compared to HDDs. While this price gap is steadily narrowing with ongoing technological advancements, it remains a factor in decisions involving extremely large datasets or strict budget constraints. However, the performance benefits often outweigh the cost premium for many applications. Beyond individual storage devices, the demands of interconnected systems led to the development of sophisticated networked storage solutions. These technologies allow multiple users and servers to access centralized data stores, enabling collaboration and scalability previously unimaginable. Network-attached storage, or NAS, is a prime example of this evolution. NAS devices are essentially dedicated storage servers connected directly to a network. They allow multiple users and devices to access and share files from a central location, acting as a private cloud for homes or small businesses. Users can typically access NAS via standard network protocols, making file sharing and backup management straightforward. NAS offers a cost-effective and relatively simple way to provide shared storage, improving data accessibility and collaboration. They are scalable to a certain extent, allowing for the addition of more drives as storage needs grow. Their ease of setup and management makes them popular for data consolidation and multimedia streaming within local networks. For more demanding enterprise environments, storage area networks, or SANs, provide a higher performance, dedicated storage infrastructure. SANs are high-speed networks specifically designed to connect servers to storage devices, making the storage appear as if it is directly attached to each server. This abstraction provides a flexible and efficient way to manage large volumes of data. SANs are designed for mission-critical applications that require extreme performance, low latency, and high availability. They achieve this through dedicated network protocols like Fibre Channel or iSCSI, isolating storage traffic from regular network traffic. This segregation ensures consistent and predictable performance for data-intensive operations. Offering high performance and exceptional scalability, SANs are indispensable for large organizations, data centers, and cloud providers. They enable sophisticated features like data replication, snapshots, and disaster recovery, ensuring business continuity and data integrity. While more complex and expensive than NAS, SANs deliver the robust capabilities required for enterprise-grade data management. Looking towards the horizon, data storage continues its relentless march of innovation. Future trends promise even greater densities, speeds, and accessibility, further transforming how we interact with information. The ongoing advancements in SSD technology stand out as a significant area of development. Researchers and manufacturers are continuously pushing the boundaries of flash memory density. This means packing more data into smaller physical footprints, leading to higher capacity SSDs without increasing their size. Concurrently, efforts are focused on improving performance, reducing latency, and extending the endurance of flash memory cells, making SSDs even faster and more reliable. Cloud storage has become increasingly prevalent, fundamentally altering how many individuals and organizations store and access their data. This model utilizes remote servers accessed over the internet to store data. Users no longer need to manage physical storage devices directly, shifting the burden to cloud service providers. Cloud storage offers immense scalability, allowing users to effortlessly expand or contract their storage capacity as needed. Its inherent accessibility means data can be accessed from virtually anywhere, on any device, with an internet connection. Furthermore, it often presents a cost-effective solution, converting capital expenditures on hardware into operational expenses for services. Beyond current mainstream technologies, truly emerging solutions hold the potential to revolutionize data storage entirely. DNA storage, for instance, envisions encoding digital information within synthetic DNA molecules. This approach promises unprecedented densities with the theoretical capacity to store all the world's data in a container no larger than a shoebox. Quantum storage represents another frontier, leveraging the principles of quantum mechanics to store data. While still in early research phases, quantum storage could offer incredible speeds and security, potentially playing a role in future quantum computing architectures. These nascent technologies hint at a future where our current storage limitations are completely redefined. Ultimately, choosing the right data storage technology involves a careful consideration of multiple critical factors. Cost remains a primary driver, as different technologies present vastly different price points per gigabyte and overall infrastructure expenses. Balancing budget with performance requirements is always a delicate act. Performance, measured in terms of access speed, latency, and throughput, is crucial for applications sensitive to delays. Capacity considerations dictate how much data can be stored and whether the solution can scale with future growth. Durability, encompassing reliability and resistance to failure, is paramount for ensuring data integrity and availability. Finally, accessibility requirements determine how easily and quickly users or systems need to access the stored data. Whether it's high-speed, real-time access for transactional databases or infrequent, long-term access for archives, each scenario demands a tailored storage solution. Navigating these choices effectively is essential for success in our data-driven world.